We're going to start off our talk of calculus by talking about the two goals that we're going to have this semester. So the first goal that we're going to try to accomplish is to figure out where a function is going. So let me back up just a hair and talk about that. What calculus does is allow us to make sense of different functions. And well, where do those different functions come from? The functions, something like y equals x squared, that's a function, and it looks something like this. Well, that function represents something. Maybe that function represents how much money we made at each year that our company was open. So we would collect these data points, we would put those into a regression and find the equation that best fits those points, in this case y equals x squared. And now calculus is going to allow us to take this function and figure out what's happening to it and what can it tell us about the real life situation. So much about this class is about making connections between what the data creates as a function and what that function can tell us about the situation. So the first goal is to figure out where is our function going. Can we control or limit or predict the output of our function based on the input? So that's the first question to answer, is where is our function going? The second question is to determine how fast the function is traveling to get where it's going. So in this area of my function down here at the bottom, my function is traveling a lot slower than it is going up there to the right. And so we want to answer that question as well. So the first question we're going to talk about today is figure out where a function is going, and that hinges on the word limit. And then we're going to ask how fast is it going, and that hinges on what's called the rate of change. And so we're going to spend our whole semester talking about those two things. Our first lesson is about the idea of limit, and that helps answer the question, where is our function going? So as we talk about limit, let's talk about the word boundaries, because when you limit things, it's very similar to setting boundaries. So think about some things in the real world that you consider that you have limits on. How about, for example, the drinking or driving age, or the length of the battery power, or your weight and height, the number of times a ball will bounce when you throw it in the air, the blowing up of a balloon, investments in an account. All of these things have limits, and we can learn a lot about a function if we know what its limitations are. And so that's what we're going to look at first. Let's use the example of investments in an account, or is there a limit on how much money you earn? If we took the interest formula and we took this situation where you have $1,000 going into an account, so the 1,000 would be your P, and the rate is 5.5%, and we're going to do this for 1 year. Now, we haven't put anything in for N yet. And N stands for the number of times a year that you want to compound your function. Or in layman's term, how many times a year do you want your interest? How many times a year do you want the bank to give you your interest? So if you wanted interest once a year, we would plug a 1 in here and here. And so you might want to pause this recording and work this out on your calculator and see that if you got interest once a year, at the end of the year you would have $1,055 in your account. Now what if we did interest twice a year? We would get 76 cents more. What if we had it for every 4 months, 3 times a year? Notice we get $1.01 more than we would have originally. And if we keep going, And if we even say, give it to me continuously, so when I say daily, I kind of mean continuously, notice that even somebody that gets their interest every day and puts that back in the bank and invests it, we're only talking about a $1.54 difference between whether the bank gives me the interest once a year or whether they give it to me every day. Well, the understanding of that helps banks in their marketing, because if they know that marketing to the public that they will pay daily interest will get them more customers, then it's only costing them $1.54 for every $1,000 invested to get your business, and it's going to be worth the bank to do that. Likewise, if you're a good consumer and you understand the limits of the interest function, then what you can say is, well, this bank really isn't offering me anything special because it's $1 difference whichever way I go, and so maybe I have to drive further to get to this bank. So that's the idea of, if we understand the limitations of this function, then we can start to understand how we might use that out in the real world. It's a little hard to graph this, but if you want to mess with graphing it, just graph it where you put an X where we were changing the numbers for n. Make sure you have your range really big, and what you'll see is that as X gets bigger and bigger and bigger, which is X is the number of times you want your interest, you'll start to see that graph hover right around 1056. So the Y value on this graph is eventually going to look like it's hovering right at 1056. So the next time you see an ad on the paper that says, come to our bank, we're going to compound your interest daily, what you can probably see is that that's not really a huge offering unless you're really talking millions of dollars. So let's look mathematically at the idea of limit. There's a lot of limit notation, but again, in the end today, what we're going to be asking is, where is our function going as we approach a certain place? So as I approach the year 3, what's happening to my profits? Where is my function going? So a couple notation things. First of all, when we talk about limits, it's denoted by the capital letter L. And back in our example, the limit itself was that ending balance of the account. So back in our example, I think the limit was right at 1056 with some change, I guess 0.54. Okay, but somewhere right around there would be our limit. And the limit of the function is in relation to the independent variable. And we call that C, that certain value. So in the example that we just had, the C, or the independent variable, was the number of compounds. So the limit of our bank account, and this is how we would write it, as X approaches C. And C, in our other example, we would, instead of writing as X approaches C like that, we would write as X approaches daily compounding was 1056. Okay? So the limit of our bank account as the number of compounds goes to daily equals 1056. That's how we would read that limit statement. That's not still perfectly mathematical, but we'll see that in a second. So here's everything again, and that's exactly how we would write it. The limit as X approaches a certain number called C equals capital letter L. And I have here too, as the number of compounds gets closer to 365 times a year daily, the account balance hovers around 1056. So that would be our limit. How close our X value gets to C has to depend on our application. Somebody that is a machinist that is working with very small parts, their value of C, or as X gets really, really close to their number, is going to have to be more precise than an astronomer who could be a couple hundred miles off and he would still get an idea of his function. So depending on what type of situation you're in is how you'll interpret the idea of closeness. Now let's look at this a little bit more graphically. Okay, in order for a function to have a limit, you must approach the same area from both the left and the right. So let me draw in an example here. And we have this function right here. And let's say that that is 3, 5. So this point right here is 3, 5. If I ask you, what is my limit as x approaches 3? And 3 could be milepost 3, 3 could be year 3, 3 could be 3 compounds of interest a year. So 3 can represent whatever your x variable represents. If I ask this, here's what I'm saying. As I travel this function from the left and as I travel this function from the right, the closer I get to 3, what y value am I approaching? And in order for there to be a limit, I have to be approaching the same area from the left as I am from the right. And in this case, as I approach 3 from the left and I approach 3 from the right, and I get closer and closer and closer to that actual value of x is 3, I approach the value of 5. So my limit of this function as x approaches 3 is 5. Now, if, and let me show you how we write this, we would write this as x approaches 3 from the left, the negative stands for left, and x approaches 3 from the right. Now, if I had a graph that looked like this, where this was still 3, and so this was my profit for the first however many years I was open, and this was my profit for the second. And I again want to know the limit as x approaches 3. Well, as I travel along this function, and maybe this is 5 and this is 2, as I travel along this function from the left, when I get really close to this 3 mark right here, my function approaches 5. So as I approach from the left, my limit is 5. But as I approach from the right, my limit is not 5. I seem to be stopping somewhere around 2. So as x approaches 3 from the right, my limit is 2. And therefore, we would say that there is no limit as x approaches 3. Around year 3, something weird happened in my company. We were going great, our profit was growing. Here's our profit growing, and then at year 3, something happened, the bottom fell out, and I dropped way down. I had a point of disconnection there, and now my function is going off on its own. So when you don't have a limit, what that says is something weird is happening in your function, and you need to pay close attention to that, because that was a period of time or place when things were not going well. So in order to have a limit, as I said, the limit from the right, so that plus sign means from the right, and the limit from the left has to equal the, or gives you the actual limit. So the limit from the right, the limit from the left have to equal each other, and then you have a limit as you approach that number. So you have to approach it from both cases. One is called the right-hand limit when you come from the right, and one is called the left. Now, you do not necessarily have to have a function value where your limit is. So let me switch colors real quick. Even if there was a hole right here in my graph, the fact that I'm approaching that level 5 from the left and right, my limit would still be 5. So the function value is the actual y value of the function at a given point. But the limit value just tells me where is your function hanging out. If you want to find your function, go look at 5. Okay? So there is a difference between function value and limit value, and you'll see in a minute that when you have both of them, that means something special. Alright, so let's take a look. And I encourage you in your graphing calculators to try this. What you would do first is in your calculator, graph y equals 4x squared. And it's going to look something like that. If you are unfamiliar with your graphing calculator, on Blackboard under Tips and Tutorials, there are some little tutorial things and links for help with your graphing calculator. So I encourage you to get used to how to use your graphing calculator. So after we graph our thing, we want to know what's happening around -3. And so if you'll hit the trace button, or if you like the table button on your calculator, and if you'll look at the values as you come from x is -5, x is -4, so if you look at your values as you're coming that way, likewise if you look at your values as you come from 2, 1, 0, -1, if you kind of flow, what number are you approaching from both sides? Well, in fact, I think you're probably approaching 36. So when you trace on your calculator and you watch the y values as you trace, these numbers, the y values, are going to get closer and closer to 36. So they're going to start up there like 40, 39, 38, 37. And likewise, coming from this side, they're going to start at 0-ish, and they're going to go up to 36. So the limit, because I'm approaching both from the left and the right, when I get really close to -3, I'm getting really close to a y value of 36. Now, if you do that with a couple of more functions, for example, this one, the limit of x approaching 3 of x plus 4, well, x plus 4 is just a line that looks like that. That heads here at 4, and here is 3. So the question is, as I approach this vertical line from the left, and as I approach from the right, what y value on my line do I approach? And I bet if you do that on your calculator, you're going to see that you approach 7. And one more example. That one is not it because that one doesn't have a function. This one right here. If we graph 2x squared, it looks similar to that other one. And here is where 1 is. And if you will trace from your left and trace from your right, you should be approaching the number 2. Now, take a second and look at your answers. Is there something that you notice about the 36, the 7, and the 2? So maybe pause your machine and see if there's something special you can notice there. Hopefully you might have noticed that 36 is actually what you get when you plug a -3 in for x. And 3 is what you get when you plug in for x here. And 2 is what you get when you plug a 1 in there. So there are, in many cases, it is true that the limit of a function can equal the function value. And so what I'm hinting at here with this example in the bottom left-hand corner is that the limit as x goes to 5 of a function can equal the function value at x is 5. You can find it simply by plugging it in. Now that doesn't always work, and in the next video we will talk about when plugging in doesn't work. But your first line of defense when finding a limit is take a look at the graph and see what it looks like. Look at where the values of the points are going around a certain x, and then try plugging it in and see if you get a value for the limit. So I have here the limit of the function can often be found by plugging in c, by finding f of c, unless there is a gap, a hole, or an asymptote. And we'll talk about on the next one what makes a gap, a hole, or an asymptote. And the approach from the left has to equal the approach from the right in order for there to be a limit. The limit from the left has to equal the limit from the right. And for a lot of this unit, when I ask you why, that's your answer. The limit from the left has to equal the limit from the right in order for there to be a limit. The last little piece on this video I want to talk about is what about the limit of a constant function. So this is a function like y equals 3, where 3 is the y value for all the x's. Well, if I want to know where this function is at x is 0, or x is 1, or x is 2, or x is 3, I know where that function is. It's at 3 every time. So the y value is never going to change, so the limit of where it is, it's always going to be at 3. So let me reiterate, and I'll just write it real big here on the side, that when we ask where something is, we are asking for its y value. When we ask for when it happened, we are asking for its x value. Okay, so where is the function is asking for its y value. When did that happen is asking for its x value. So the limit of a constant is always a constant. So no matter what, the limit as x approaches 5 of the function 12 is going to be 12. It's always at 12. That's what that function is. So take a second and review these notes on the introduction of the idea of limit, and then there's a second video for you to watch to wrap up limits, and then a short one to watch also on continuity for this first piece of the introduction to calculus.